let us start with our first slide, that is iterated hash function. See, iterated hash function is nothing but we will be we'll be creating the message digest once of of fixed length from the variable size of input. Then after getting a particular output, again we will be giving as an input to the next hash function to provide again fixed length of output. So this is what the iterated, the repeated process of giving to the hash functions. Right. So let us write in a smaller way that if my message is there of some 520 bits, I'm giving this to hash function. My hash function can give, let us consider 64 bits. Now what I am doing is I got my message digest of fixed length, that is 64 bits. After getting this, I will again give this to the hash function. Okay, I will again give this to the hash function. Again, 64 bits will be again given to the hash function and it will generate some other message digest and given as a message digest of the 64 bits. Right. So here we are comprising, even though it is giving 64, 520 converted to 64 and again 64 converted to message digest, and message digest is an input again to the hash function. So we perform n number of times to overcome the collisions part, So where we discussed in the prior sessions about there are collisions where many to one. So n number of messages can give same message digest. So if we are repeating like this, we won't get a repeated type of hash codes, the message digest, right? So this is what the exact structure and iterated hash function will be having. Here we have input message M. That message we are giving to the compression function. So that is a hash function exactly. See, large number of data we are giving to the hash function. So it is providing us a fixed length of output, See, this is a vast data we are compressing with the hash function and we are getting the hash code here. So whatever the hash code of fixed length, we are giving again as a repeated loop back to the compression function. See, here we are saying always the compression function because the message of larger bits are converted to the very fixed, very smaller and fixed length of data, right? So this is what the iterated function is, the repeated looping process of the message digest with the hash function happens, right? And the next one is a Merkle-Damgård scheme. This scheme is very, very important to know. This is one of the iterated hash functions. See, we have discussed the first hash function, then iterated hash function, and then with the use of iterated hash function, we have one scheme. That scheme name is Merkle-Damgård scheme. This scheme will be utilized to overcome collisions. So the main aim of Damgård scheme, Merkle-Damgård scheme, is the collision resistance. We are overcoming the collision attack. So in this also, we are going to take n number of, the message as it is, and we are going to convert that into the blocks. Okay. So every block will be having equal sized bits of data. Then whenever at last, if the bits are not sufficient, we are going to pad the data. Extra bits will be padded. Next, M1 will be created with a digest and then given to the compression function H1. Okay, so thus M1 will be operated with H0 prior to this itself. M1 will be operated to H0 and will be giving as an input to the H1. So in this point, we have this, I guess. The digest H0 is set to the fixed value called IV. So IV is nothing but the initial value. So this initial value is nothing but the H0. This H0 will be calculated with M1, first block, and these two, the combination of M1 and H0 will be given as input to the H1. Got it? So let us see the diagram so that you can understand in detail about this. Yeah. This is a diagram. Whatever the message we have, original message, convert that into equal sized block of data. See, n bits, and every block will be having n bits. So if at last, if the message is not sufficient with the n bits, so let us go with, if we are taking 64 bits, 64 bits, and we left at last with 31 bits, we are going to pad plus 33 bits. Okay. So that is the part of padding, and we'll make the bits as n bits. So after making equal sized blocks, then we will take the initial IV. So just now we discussed IV is the initial vector or the initial value. So take this m bits from the key or else any random value. Then you take these two values, m1 and h0, provide to the h1. Okay. So see here, h0 and m1 provide to the h1. So here the function which we are going to apply is called as a compression function. Now this output of h1 and m2. See, if we are at hi, m will be at mi plus 1, or else if we are at mi, h will be at hi minus 1. Okay. So this is a small thing which you can understand very easily. Right? So like this, till we complete all the blocks, till we complete all the blocks, we will be generated with the hash values. The last block ending point is called as a message digest. So with this message digest, we can frankly say that there will be no collisions happens maximum. So the collisions are taken place when we are doing hashing only one time. So to restrict that, we are repeatedly doing this. I mean, iterated with this. Got it? So this is a Merkle thing. Now the introduction part of the hash functions. The introduction part of the hash functions are very important because there are three families, MD family, Whirlpool, and the Shah family. Out of all this, only out of all the families, MD family is ignored nowadays because of a small disadvantage which it has about the collision. So it has faced collisions, and thus this is outdated one at present. Okay, MD family is outdated at present. Even though if it is happening also, MD5 nowadays, some applications are utilizing it. Got it? Now, Whirlpool and Shah plays important role. So let us discuss about MD first, then we'll move to the other one. See, this is the MD family. In the MD family, we have three variations, MD2, MD4, and MD5. MD2 and 4 face a lot of bit size variations. So thus we have moved for the MD5. So MD5 takes 512 bits of data, and MD2 and MD4 are very less, I mean 256 and 128 and 64 combinations only. Thus we have moved to MD5. So MD5 can take blocks of size of 512 bits each. So one block can be 512 bits and creates the hash function digest. I mean the output of hash function as 128 bits. Message digest can be 128 bits. And the message size can be 512 bits. Got it? So this is message size, and this is a message digest size of MD5. MD is nothing but message digest. Now, see, 128 bit size digest is too small to resist collisions. Okay. So these collisions took place a lot, and thus the MD5 has been failed actually to say. Then after we got to know about Whirlpool. So till 2000, like that, MD5 played well only. Then after we entered into Whirlpool. So in the Whirlpool, it has been introduced with AES algorithm. Okay, so along with the hash function concepts, we have included the encryption standards also in the Whirlpool. So thus AES entered into the scenario. So in Whirlpool, we can take a hash digest as 512 bits. See, this is very large, 512 bits of digest. Message digest itself takes 512 bits. Till now, till MD5, whatever we have seen is maximum 128 bits only. Digest. We are talking about the message digest. 128 bits of message digest till now. After Whirlpool enter with the AES concept, we have extended that to 512 bits of message digest. And message size also, I mean the initial message size also, every block size also will be 512 bits only, right? So this was introduced by Ridgeman, and who has a greater communication with Ridge and L. So thus the combination of Ridgeman and Ridge and L happened with the hash function and encryption standard. Thus, Whirlpool is a combination of both hashing and the encryption. This is the only algorithm which is having combination of both hash function and encryption. Thus, and this is very strong enough, and we don't have much, we have not faced much attacks with the Whirlpool. Thus, it is strongly built in the network nowadays. Also, it is working very well. The only thing is we have to include extra complexity for including hashing and encryption at the same time. Okay. So we are taking a whole 512 bits of data and we are padding where if we require, we are padding extra data and along with the message length to match with the message length. After this, see, first 512 bits, second 512 bits. So like this, nth 512 bits we took. Now what we are doing, HIV. So IV is nothing but the initial value, right? Initial vector or initial value. So as similar to the iterated function concept, Merkle-Damgård concept, what we took is the initial value of 512 bits, all zeros. See, all zeros. Okay, initial value will be always all zeros. So you may be having confusion, what is this H0, where from it has come. So H0 is nothing but all 512 bits are zeros. Now you just take that 512 bits, apply AES algorithm as a Whirlpool cipher. Here we are taking 512 bits, right? So as per AES concept, we can have 128 bits only. Yes or no? So for this 128 bits, we converted this 128 bits into a row concept, that is 32, 32, 32, and 32. Right. So each state will be giving, each row will be giving 128 bits of data. But as here we have 512 bits of data, we are making every word size as 64, 64, 64, 64. And this is not a 4 by 4 now. In the AES standard, it is 4 by 4. But here it is 8 by 8. Here it is 8 by 8. So 64 8s will be getting 512. Okay. So 512 bits of data will be occupied in 8 by 8 matrix. Okay. So 8 by 8 is matrix. Every slot in the 8 by 8 will be of 64 bits each. So 64, 64, 64, 64, 64, 64, as this will be 8 times given, right? So Y means every row we will take one time. So first 512 bits, operate something and convert to the second 512 bits. So this is what we are doing in the Whirlpool concept. So what we are doing is H0, apply encryption algorithm of 512 bits. So whatever the output we get, whatever the plain message text we have, and whatever the H0 we have, all the three do XOR and give to message 2. Now what message 2 is doing? Take message 2, the output directly message 2 and encryption procedure of this, and the output, whatever the cipher we got, and the H1 value give to H2 by XOR operation to the next slot. So this will be repeated till end of all the 512 combinations, and then whatever the final value we have will be of 512 bits of message digest. So this is a working structure of Whirlpool. Got it? This is the working structure of Whirlpool. If you have any doubts in this, please be free to ask me in the college or through comments. We'll be including SHA family in the next session.